Go. Okay, Mr. Jeet, do you have a question? Since you're here, I'll make you first in line. What you got? Anything? All right. Oh, no, not at the moment. Okay. Anybody else? You can enter them in the chat box, or I have my volume on. You can speak up. SQL versus NoSQL. Okay, good. That's an excellent topic, madam. Okay, so they're both going to store data, right? So SQL, and we don't mean SQL itself, right? Because we know SQL is a database language, right? For relational databases. NoSQL is basically a class of non-relational databases. So what we mean by relational, the big thing is the tables are related, which means the essential consequence of that, which means you can run queries that span multiple tables. Like again, if you have a table of customers and a table of invoices with tables of customers and invoices, you can run queries involving both tables, like which customers from zip code ABCDE have bought item XYZ in, I don't know, in December. Okay, something like that. It integrates data from both tables. So that's what relational databases are. And the essentials, let me look, make sure I'm answering your question correctly, what they store. Okay, so relational databases, remember, are like MS Access. So they have some key attributes, right? All fields, right? So each field within a table has a format that applies to all rows in that table, right? So for example, zip code might be, you know, a 5-character text string with a numeric mix, or, you know, possibly a 10-character string, right, like ABCDE-FGHI, right, with a numeric mask and hyphen, or just a number, right? But whatever it is, whatever format you've chosen, that's going to apply to all things. Okay, so that's the basic structure of relational databases. And the handy thing about them, because the fields are uniform across rows, right? The field formats are uniform across rows. Queries involving multiple tables get processed quickly because the system knows exactly where to find the information and knows that it exists, right? Compare that with a key value store, right? Again, in a key value store, since the field formats aren't going to be uniform across rows, if you try to do a query involving multiple tables, then one of the problems that happens, you have to look in every record to see if that field is even there, okay? Because you don't know, because every value could be a different type. The other thing, limitations, right? When the tables get very large, you know, in particular, spanning across multiple hardware, right, data storage devices, leave that. The queries can be very slow, to execute, because all that processing and comparing involves lots of data interchange across the network, right? Which is much, much slower than a machine's RAM. Okay, so that's all the takeaways from SQL, right? That's the key stuff you got to know. Now, NoSQL, basically, there's a variety of ways to do it, right? There are multiple ways to implement NoSQL. I should also add, I guess, the last thing for SQL. Generally, these follow our ACID properties, right? So generally these systems, these relational and database systems, follow ACID properties. That way we know the correct data is always there. But again, big systems get slow. Okay, so multiple ways to implement NoSQL, but they all involve cutting some corners, typically either, for example, multi-table queries aren't feasible, right, because they're going to be too slow, or not holding up all ACID properties. Okay, for example, like Facebook's, Facebook's photo management system, for example, right, with eventual consistency. So Facebook's photo management, or let's just leave it as the system of likes, and what are the other things for emoticons? What are they called? Emotes, whatever. Okay. So things like that. That's what NoSQL options are. And generally, basically, NoSQL will try to improve database performance, right? Which typically means faster query processing by giving up some capabilities or guarantees of relational database management systems. Okay, so that's pretty much it. All right, so that's it. Google database systems. All you got to know for Google's database systems. Okay, so that's one thing. There's 4 big ones, as I recall. Let's see. So Spanner is the big database system underlying everything, pretty much, at Google. Okay. The next one is F1, is the big database for ads. Okay. Then we have Bigtable, which is a specialized database used for storing distilled web page data, among other things, right? And so we have a few key attributes there. So number one, column families. A column might represent not just one attribute, but a group of attributes by holding a reference to that group information, right? A link, basically. Okay, that's one thing. The other thing is sparsely populated. It is designed to group together sets of empty rows to maintain space, right? To conserve database, to conserve data storage space. I don't know why, storage space. Okay. Which again, I'll add, which at Google scale becomes significant. So like if you're an ordinary operation and you have like, I don't know, a few hundred terabytes of data, sure, a few hundred of those hard drives, solid state drives, maybe $100 each, it's going to cost you a few $1,000s. And, you know, if you waste some space there, yeah, that's unfortunate, but it's also not that big of a deal, right? If you're a reasonably large operation, $4,000 is kind of like nothing. So, but at Google, right, one of their big bills is all this data storage space and all the operations to check it and all the electricity that has to be on and available whenever this stuff is available. If you can scrunch down that data, the data storage requirements, that means not only less hardware, which is significant, but also less electricity to keep it all up and running. Okay, so that's big table, right? So we know Spanner, we know F1, we also know BigQuery, which strictly speaking is not a database system, but still it is a system similar to Hadoop or MapReduce that typically decomposes very large query operations, right? So for example, queries on tables involving basically 50 million or more rows into a set of much smaller subproblems and returns the results much faster. Okay, so that's BigQuery. Those are the ones you need to know about. The whole question of whether they're SQL or NoSQL, in general. Okay, so generally you can use ordinary SQL on these, right? Especially on Spanner, which Google uses to run transactions for other businesses in its cloud. Right, its cloud system is well, Google's cloud. Anyway, so it uses ordinary SQL, but Google itself generally uses an extended version of SQL, right? Basically, SQL plus some other capabilities for its own special needs. All right, but it wants to make ordinary SQL available so that a business doesn't have to change all of its database code in order to run its stuff on Google. Okay, so I'm going to insert that here. Google uses to run, so businesses don't need to rewrite their database code if they migrate the operation to Google. Okay, so there you go. All right, so those are the database systems. And let's see, I saw there was another question. Index system components. Well, I can walk you through the process, right? I mean, this isn't super technical because, well, for one, Google is a little bit, what's the word? They're a little bit cagey about giving out too many details. They don't want to tell everybody everything about all their special sauce, right? When you find stuff that tells in detail how Google does something, generally it's going to be 10 years old. If you find something like within the last few years, it's going to be like, you know, a PowerPoint presentation level of detail. It's going to say, here are the things that Google does, and that's going to be 2/3 of it. And then they'll have a little bit about, you know, and we use modular applications inside our data centers, and our people are great, and they don't really tell you anything. So, but we'll talk about the index system components. So I'll walk you through the process. Okay. So again, here's the whole thing. We'll do it from the start to the end, and here's where it all comes in. So Google side, they periodically, should be a Y there, periodically send out Google bots, right, which are also generically known as spiders, to search the internet for web page updates. Okay. When a Google bot finds a new version of a page, what does it do? Well, it reads the page and sends that information to the index. Okay, and of course, and then follows any links on that page to likewise check for new or updated pages. Okay, so that's how Google gets this information. On the index side, when the index receives a page, right, there's a few things that have to happen. Number one, the page's raw data is stored in one system. Okay, all of these web pages, yeah, Google has a copy of the whole thing. This is a useful starting point for distilling data and also for testing new algorithms for delivering search results, right? Which if you didn't have the whole page there, you wouldn't be able to test features that aren't, test variables that aren't already stored in your databases. The other thing, number two, key important elements from the page are distilled and entered into Bigtable. Okay, so that's the other thing. So all of that data sorted into Bigtable with a timestamp. So Google knows which is the most recent data. Okay, and eventually it'll go through and prune some of that really old data that isn't needed anymore. Okay, so that's what the index has. It basically has two things. It has the raw version of the page that Google uses, number one, to distill data from it, and number two, long-term, Google can use that for things like redesigning its search algorithms. And number two, the important elements from the page, Google keeps them distilled and in a database. The reason is, with this separation of 1 and 2 is necessary so that Google doesn't have to redo the distillation process every time someone does a search, right? Because many pages, most pages, whatever, will show up many times in search results. And it would be a big hassle if you had to compute all that from scratch every time. Okay? So that's the stuff that goes on the indexing thing, on the, on Google side. So all this data is there and it's available and it's waiting for somebody to come look stuff up. Now, the other part, what happens when a user enters a search query? Well, when a user enters a search query, first of all, Google checks the index. Well, I'm going to say the first thing, Google parses the query into likely term groupings. Okay, and we can discuss how that does it, but that becomes kind of a weird technical thing. But essentially, if Google is doing something like New York restaurants, if that's what the search query is, then, for example, then New York is probably a much more likely grouping than York restaurants. Okay, and Google's going to know that. So that's going to help Google streamline its search efforts, how it combs through the index. So anyway, Google checks the index with those likely term groupings. Okay, and Google's going to say, aha, I found when it finds, okay, so the first thing, it's going to check the index for the likely search terms, and it will gather up a group of pages that contain one or more of those terms or their semantic equivalents, right? So it's not going to turn up a completely unrelated page, but you don't have to have every word in the search query actually appear on the page, and you could have different words that mean the same thing. Okay, so for example, you know, what would be something like, what would be a good thing? I don't know. Coca-Cola would probably be about the same as a can of Coke, for example. Something simple like that. Anyway, so we find semantic equivalents for these terms. Another thing, also, Google will check for misspelled terms, right? So anything that is an uncommon search term that is very close in spelling to a common search term, right? That's most of how that works. And of course, it's all relative, right? So you might have a common misspelling like separate, S-E-P-E-R. You could still get like 1 million hits for that, right? Because it's such a common misspelling, but it's going to be probably much less common than the correct spelling of S-E-P-A-R-A-T-E. Okay, so that's that. And those pages containing those terms will also be included in the results. Okay, so at this point, after doing all this, I'm going to box this up in green. I'll box it up in blue. After doing this, Google has the set of pages that must be ranked prior to delivery to you, the user. Okay, so Google has a set of pages. The next thing it has to do rank the pages. How is that done? Well, if it's a popular term or terms, there could be billions of matching pages. You're not going to get those billions of matching results. Okay, so instead, here's what happens. Here's what happens. Each of many servers processes a slice of the relevant index entries and finds the top 100 or so matches, okay, based on factors like co-location of terms, right, if they're actually located next to each other. What else? If frequency of terms, okay, term sequence, are they in the correct order, and user click behavior, right? And I'll say global, let's say global click behavior, right? Who all has clicked on what pages? So that sort of stuff is what all goes into determining how Google is going to deliver search results to you. And I'll say, and in many cases, your custom tracked behavior as well. Okay, So each of those servers gets, maybe 100 or so. Those 100 or so best results are combined and, again, ranked against each other to give you the set of perhaps 200 or 400 top results, which are, again, actually delivered. Okay, so that's the process on Google's side. A search query gets entered, Google parses it up into what it thinks the most likely term groups are. It's going to check for spelling errors. That'll give it some alternate index entries, and then it's going to combine all of those together, give you all the pages containing all the terms as an option. It'll rank them against each other because Google's not going to deliver the hundreds of millions or more pages. It's going to try to find like a couple hundred or so. It's going to deliver those. So it's going to rank all those pages against each other. It's going to do it on a whole bunch of different servers, so it happens in parallel, right? So I'll make a note of that. This process happens on many servers at once, so results are returned much faster due to parallelism, okay? Because you have a bunch of servers working in parallel at the same time to deliver the results. And then that's what you get at the end. Okay. BigQuery in more detail. I mean, I could explain BigQuery in more detail, but you don't need a whole lot more about it, right? I mean, I'm not going to ask you how, but if you want, I'll take a minute. I'll explain some stuff about BigQuery. Sure. So the basic way something like this works, imagine hypothetical but fairly typical BigQuery case, okay? Imagine that you have two very large tables, right? Each, I don't know, how large are we talking? Two very large tables. Let's say they're so big that each span across two hardware devices. Okay. So we have two very large tables, and that's how it is. They span across two hardware devices. Got it. Good. Now, a query involving those two tables could run very slowly. Why? Well, let's take a look. So I have two machines where this table is, all right, and I have two machines where the second table is. If I want to cross-check, if I want to cross-check everything on on both tables, I can't just put that in RAM. Okay, I can't. It's so big. It's on two. If it's like terabytes of RAM, heck, I mean, even if they're not on separate machines, even if it's just too big to get processed at one time in RAM, it could be pretty slow. So, but these two tables, these are very large. If I want to check everything, I can't just put that in RAM. It'd be too expensive to set up, say a 4 terabyte RAM system. That would be very, very expensive. So I have to send communications back and forth between the machines and wait for them to be received and wait for the responses, and hopefully nothing else important is going on in the network to slow that down. Okay, so there's going to be a lot of back and forth. If I have, like, let's mark it in here, this row, right, whatever's in that row, I got to check and say, oh, what is this one in here, right? And I see, oh, is that a matching result? And then I get this next one. I say, oh, is this one a matching result? And this one, is that a matching result? And I have to do that back and forth through the network for every record in the tables. Okay, it's going to be very slow. If I could put all this stuff in RAM, if I had some massive, multi-terabyte RAM system, yeah, I could do this a lot faster. Or if I had some special parallel system, then I could do it a lot faster. Process ordinary businesses, right, that might be good at, say, delivering packages or making cars are not necessarily great at this sort of, distributed database design. It's not their core business. But for Google and others, right, like Google, it is. Google is absolutely in the business of managing this kind of distributed database design like we talked about with the index. So with Google, they don't have to build, right? Google doesn't have to build any sort of specialized new system for this. It's just what they already have in their own BigQuery system that they use internally already. All right, so that's the base. I hope that kind of makes sense. I mean, I could get into the details of like typical things that how BigQuery actually works, but basically what it is, if you have some really big tables, Google is able to break them into smaller tables and, right, subtables. I'll just say small. This is my hyphen. Small subtables and run the query very quickly. That might take the owning organization, days to run. Okay, so that's basically it. Okay, retrieval for sorted and unsorted data. Excellent. Well, key thing to keep in mind, anytime you have unsorted data, it can take a long time to find something, right? In general, you have to scan through the entire pile of data to find your thing, right? About half the pile, if it's actually in there, and the whole pile if it isn't. Okay? So, simple example, phone books, right? For example, if I want to look up the phone number for a particular address, right, which is not how phone numbers are indexed, okay, I have to scan through the entire phone book to find it, right, which is a very, very long and tedious and error-prone operation for a human, right? For electronics, just long. All right, so that's what happens if you have unsorted data. You don't have a way to find the stuff easily. If the data is sorted, for example, I want to find the phone number for a particular person, which is how the phone book data is sorted, then that's easy, right? I go to the appropriate last name section, flip a few pages to actually find the correct page, scan the column to find the correct entry, which is fairly quick, even for a human, and for devices, blindingly fast for machines, or at least electronics. Okay, so that's part 2. So, unsorted data, difficult to search. Sorted data, very easy to search. Now, the question is, what about data that is fundamentally unsortable, not just unsorted, right? What about that? Well, that's what Google is trying to solve with its indexing system. That's what it is. So, because web pages don't lend themselves to easy sorting, right? There's no way to clearly say this page is more, right? Or, you know, ahead or after this other page. Doesn't make sense. A different method is needed. And for Google, that's indexing. So Google largely solves this problem through indexing based on page text and ranking based on text and other factors. Okay, so not only can it find something pretty easily, all things considered, right? It says, oh, if this page has these terms, it'll show up in the index, but also it can run the query and quickly return a set of appropriate pages based on a search query, right? Which is much better. I'll add much better and faster than searching the entire internet for every search query. Okay. Good. Other stuff? How's everybody doing? What's happening? Any more things? Questions? Things, not strings. Yeah, okay. So, hey, there's that same thing, right? 2 people at the same time. Great. Okay. As they say, 2 birds with 1 stone. So, things, not strings. Okay, so to understand what this is, first you need to know what a string is. So a string is a generic computing term for a slug of text. Okay? Here, it means literal, exact text matches. That is, the page won't show up in the search results unless the match is exact with the search term. Okay, things, of course, we know what things are, but things here, Google is trying to find semantically equivalent terms for the given query substring. Okay, basically terms that mean the same thing even if they use different text, right? So an example of that, you know, you might have some overlaps. So simple thing, let's say, what would be I'm thinking something. I'm trying to come up with some medical stuff, but it's not really coming to me right now. Well, let's say, what is a semantically equivalent term? Oh, yeah, okay, like the highways in Chicago, right? So what's I-94? The Kennedy Expressway. What do we call that one? I-90, I-94. Oh, that's the Kingery, Chicago. Okay, yeah, I-90, I-94. Yeah. Okay, so that's fine. Like common names for highways in Chicagoland. Okay, I-90, or a segment of it anyway, is equivalent to the Kennedy Expressway. All right, so what you don't want is, for example, the problem. I'll put the problem in red. You don't want people to miss out on very relevant search results just because one page refers to a concept with different language, with different terminology. Okay, that's the basic idea. So, things not strings as an operating principle means that Google will accept some variation in, some deviation from exact text matches in order to return more relevant search results. And the key thing here, right? What is acceptable deviation, right? Well, the basic logic of it, if two pages using different terms are about equally clicked, right? Two different links in search results, so two different links in search results using different terms are about equally clicked. Then Google will understand that they're probably semantically equivalent. They mean the same thing, right? It's a behavior-based thing. Google doesn't really have a good way to know otherwise, right? I mean, you could program it with some human-type guesses, but you don't want to do that for everything. So again, if people are clicking on the same things a lot, or, here's another one, or simply if two search queries often follow each other and lead to some identical pages, right? Some identical results, they might also mean the same thing, right? Because Google understands if I look for I-90 and I don't find the thing that I'm looking for, and then I look for the Kennedy Expressway, which is a particular segment of it, then Google understands that there might be some relationship there. And if there's a lot of interaction with the pages, right? For example, if one page contains both I-90 and Kennedy, and people click on it about equivalently, right, for different searches, different search term sets, again, Google will learn that the terms are equivalent. Okay, that's the kind of thing that's going on inside Google. They're trying to figure out the meaning of terms. They're basically doing it by machine learning, looking and seeing if people who entered different search terms are going to the same place. And if they're going to the same place, then as far as Google's concerned, those terms mean the same thing. And then, last, those semantic equivalencies become integrated into the index, right? So that, basically so you don't have to duplicate stuff too much. So that search terms, so that index entries are less redundant, right? You don't keep multiple copies. And more inclusive, right? It's better to have the index entry for, say, I-90 also include everything that has Kennedy, and perhaps vice versa as well. Okay. Let's see where we are here. Database joins. Okay. Well, a database join operation is just pulling data from different tables. Okay. So there are multiple ways to do this, right? But the big two, for example, are inner join and outer join. Well, they're not the only two. So let me give a simple example since you asked. Now I'm gonna mention this level of detail is not really required for the exam, right? So if you know what a join operation is and basically what it implies, then that's enough. I'm going to explain to you what it is. Maybe it'll make it stick a little better. So imagine if I have two tables, right? And I want to run a query on both of them. And each of those queries, right, involves some subset of rows. So in an inner join, basically, if I apply, when I'm compiling the query results, I have this set of data, this row, and this one. This is how I find all the matching results. I'm gonna explain why in a second. So run the query, finding all matching rows, right? Then extract the matching row pairs, and right, that's the first thing we do, and then show the fields specified by the query, right? So for example, if I have a table here with customer and it has a bunch of data, but all I really want to show is the ID, and this might be invoice, and what's relevant here is some particular item and a date and a zip code. Okay, and perhaps in those, right, so here's all the information I'm going to have. I might just say, okay, here's all the rows from the customer record, but the things that I want to show are the set customer.id, right, invoice.item, invoice.date, and invoice.zip code, right? And that's going to be what's specified by the query whenever I write it in SQL, right? So show customer.id, invoice.item.date.zip code from customer, comma, invoice, where, and then whatever the search criteria are. Okay, so that's an inner join. And you can see that if you write some of these queries in SQL, or you just do them through the wizard in Access, then you'll see them as various join operations. An outer join is more complicated. It's more sort of a nightmare. So I'm gonna undo some of this. Okay, so imagine that you have two tables that you want to check for referential integrity, right? Basically, verify that any foreign key used in one table, in fact, any foreign key value used in one table, in fact, exists in the other table. Okay? Well, in order to do this, what's going to happen in the extreme case, so again, you have two tables. What you'll do is for every row in this table, you're going to have to check the entire table. And to do this as a single standalone database operation, basically you have this. You have this, whoop, and this together, but you have to do this combination for every record in this table. So instead of just doing it once, right, if there are if there are, 1 million records in the first table and 1 million records in the other table, you're going to have to do 1 million times 1 million records. It's going to be a huge operation. It's going to take a very long time, especially if these things are on different hardware, right? And if you don't have RAM capacity to process this. So anyway, that's fundamentally what an outer join does. Now, of course, right? Of course, you don't have to do it that way. There are shortcuts, but you might not get those shortcuts in ordinary off-the-shelf software, right? You might need to design or rent a specialized system to do this, let's say to do this in an optimal way. Okay, but that's what inner and outer joins are. Again, join operations are just taking data from different tables and combining it in some fashion. There are reasons why you do it. Again, outer join is typically done if you want to cross-check everything in two tables, make sure that all the records actually exist, then yeah, that can be a big headache. Okay. Knowledge graph, yeah, okay. Essentially, the knowledge graph is sort of is a way of what shows the quantifying relationships between semantic terms. Okay, and the results are displayed in what are called knowledge cards. So the example I like to do, if I do something like, I go to Google and I'll say famous astronomers. Okay, there is a knowledge graph that recognizes that these are people who are astronomers. So, you can come up with a bunch of different membership options for this. So first of all, people, right? People have professions, right? And one profession is astronomer. Okay. So if you have a long list of people, you can scan through that and say, oh, yes, astronomer. That is a kind of profession done by people. I get that. What else? What does it mean to be famous? Well, famous is probably going to be represented, right, in someone who keeps popping up in history or searches or on pages, right? Somebody who's well-known, famous. Google is going to understand what that means. So how does it integrate these two? Well, there's a few things, right? All astronomers are people. We're also looking for famous people. So Google can combine these two terms, bum, 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 right? And say, generate a list of people known to be astronomers who are famous. There it is. Okay, that's the idea. And so Google doesn't have to find pages, right? That's the key point. Google doesn't have to find pages that specifically include the terms famous and astronomer, right? It can know or learn those from other methods. Okay, so once Google knows that, oh, Galileo, for example, is an astronomer who's pretty famous as astronomers go, the page itself about Galileo doesn't have to say famous astronomer for him to turn up in the knowledge cards. Does that make sense? I hope it all does. You're welcome. Anyone else? You're welcome. All right, I guess the popcorn bag is done popping. So I'm going to wish everyone a good weekend and study up for the exam. Good luck. This will be available, by the way, in maybe an hour or so on Blackboard, and I'll post it up on YouTube later. All right.